That will allow you to finish up the last couple problems on homework 4, turn your attention, if you haven't already, to studying for the exam. That will be 1 week from today. Tuesday will be reserved for getting a chance to see me in person during the midst of your studying, and as well, I will be lecturing on new material on that Tuesday of next week as well. Are there any quick questions before we jump in? Okay, so we have one thing that we were in the middle of last time. How can we make our capacitors better? And we found that there was some limitations. Here's your formula for computing the capacitance. The factors that go in are the plate area, that's the area of each plate, the plate separation, and then also we found that we can improve the capacitance greatly by putting in a material between the plates called a dielectric. The dielectric constant of the material is basically the multiplier on the capacitance. So if you can find a material that has a kappa of 2 or 3 or 1,000, you can get 2 or 3 or 1,000 times the capacitance, improve the storage ability of something 2 or 3 or 1,000 times by putting it into between the plates. Let me remind you what kappa ultimately is. Kappa is how much the net electric field is reduced from what it would be otherwise. So whatever the plates themselves would produce, you divide by kappa, and that gives you the net field between the plates. This is, again, comes from partial shielding. So for instance, if kappa is 3, that means the net electric field between the plates is of only 1/3 of its value that it would have been otherwise. Okay? So for instance, if kappa is 3, then E net is 1/3 of what it would be otherwise. Okay? So, for instance, what that means then is that if the net electric field is only 33% of what it would be, which of course means that you have shielded off, I don't know if that's proper grammar, but shielded off 66%. So the E induced shielded off 66% of the field, okay? So that's just as an example. And hopefully it doesn't bother anybody that I'm using 33 and 66. I know that I don't add to 100%, but I don't feel like doing the repeating decimal, okay? So that's basically the deal with dielectrics. We quantify their shielding with kappa, and the whole idea, just to summarize last lecture, was the idea that if you shield off this electric field, and basically going along with it, suppressing the voltage, that means you have to put that much more charge and energy onto the plates before it gets up and is quote unquote full. So we go over here and we see again how we're going to make the best storage device possible. We find a material with a large kappa. We make the area of the plates large within reason, obviously, that larger is not always better. And then the last one, that was the one that we left off with, where we say when we bring the plates closer together, we make it better, which seems like a win-win situation. We get to make it smaller and better, but there's a catch, and that catch is, let's go over that right now. So here's what I have. I have a battery. I have it attached to a capacitor. Then, same battery, but I bring the plates closer together. Okay? So I didn't bother to put a resistor in there. A resistor, of course, would stretch this out to an exponential charging situation. I leave off the resistor, and I can just basically pretend that all the charge just goes on there immediately. So here's what happens with this capacitor. We get plus and minus charge. This capacitor is not that good because the plates are far apart, and so it doesn't get that much charge, and those charges do not make a very large electric field. So I might draw this electric field that they make between the plates, with the lines fairly far apart. So I'm going to only put, say, 3 lines across here. All right? So now I've brought the plates closer together. I made it a better storage device. And accordingly, there will be more charge. So I'll try to draw lots of little tiny spaced charge here. So there's lots of charge on each one. So there's more charge. So this is a better capacitor. It stores more charge. So I guess let's say better capacitor because the D is lower, the plate separation is lower. It stores more charge at the same voltage, same effort, of course, provided by the battery itself. Well, if you have more charge, you'll have more electric field from the plates. The plates themselves will make a stronger electric field. So let me draw that. I'm going to draw a very small, tightly spaced electric field to indicate that the electric field is very strong. So we have a strong electric field caused by more charge on the plates. Again, why is there more charge on the plates? It's a better capacitor. Here's another way to reason it if you want. If we look at the relationship between electric field and voltage. We used to write it like this. You used it like this on a homework number 2. And last lecture, I think we briefly looked at, hey, let's just change the notation a little bit. Delta V we call V, and the delta R over which it changes is just the plate separation. So here, this is fixed by the battery. The battery is holding the voltage difference across the capacitor, always whatever it is. But now, rather than E being proportional to V because D is fixed, that's not what we have now. I used that last time. I was putting the dielectric in and out, but I wasn't changing the plate separation. But now, if I decrease the distance, I do indeed see that the electric field gets stronger. So it's nice to see you have several different reasoning mechanisms to get the answer that when you put the plates closer to each other, the electric field gets stronger. So the plates will produce a larger electric field. All right, so remember that we do have some material between the plates. So remember we have our ice cream filling in our ice cream sandwich. There's a dielectric in there to which this electric field of the plates is being applied to, right? That's what initiates the partial shielding in the first place. So let's take a look. If I call this scenario A and scenario B, let's go ahead and draw those and compare them over here, A, B, and we'll put a weak field over here, and we'll put a much stronger field over here for comparison's sake, okay? And, of course, we're going to now see how do those electric fields affect the material itself. What is the material? Well, in the dielectric, what we have is a positively charged nucleus with electrons all around it. And of course, before you do anything to it, there's going to be all of that minus and all of that plus is basically going to be coincidentally all on top of itself if we assume that there's no permanent dipole moment. You guys know what that means, right? Okay, so unless it happens to be a polar molecule, let's say there's 0 dipole moment, okay? But you can have what's called an induced dipole moment when you apply an external field like this. So here's what happens. This is one of these nuclei and one of the atoms in the dielectric, and the minuses are pulled off a little bit to one side, which I've been drawing like this, just for shorthand. So the electrons are pulled off center. We have what's called an induced dipole. And of course, now that we have this is what produces E induced, right? that's where E induced comes from, is the morphing of the atoms in the material. Okay? So remember, if your material has a kappa of 3, that means that E induced has to shield off 66% and leave a third of what's left over. So whatever this is, E induced has to shield, say, I'm just using those numbers because it's easier than talking in the abstract. Let's say you have to shield 66% of the E external from the plates. So that's your job. So let's go over here. Well, if your job is to shield off 66% of the electric field from the plates, well, that's going to be a harder job now, right? Because if you shield off 66% of a larger field, that's going to be a bigger job, right? So the only way that can happen is if something like this happens. Here's the nucleus. Now the electrons get pulled way more off-center. Just to greatly exaggerate like that. And just for kicks, I might abbreviate it like this. So we have a much larger induced dipole moment. Again, that's where E induced comes from. And now, basically, in order for you to shield off 66% of a larger E external, well, that's going to mean a larger E induced. So if your job is always to shield off 66%, well, would you rather have 66% of $1 or 66% of $1 million, right? That's not the same amount. So where the dielectric has a larger job to do now, because the external is larger, because the capacitor plates are close together, then E induced has a larger job to do. And this gives you a hint of what's going to happen. What do you think is going to happen to this atom eventually? Right? At some point, this is just going to snap like taffy. The minuses are going to go their own way, going upstream to the field, and the pluses are going to go down. You're literally going to tear apart the material. And this is called dielectric breakdown. Question?
Is that what's happening? You were talking before about splitting in like thunderstorms?
Yes. So dielectric breakdown is what happens in lightning. So this is called dielectric breakdown. So dielectric breakdown is when the external field exceeds a threshold and the dielectric is literally torn apart. Anything will become a conductor if you try hard enough, even if you have to forcibly tear the electrons that are bound to the insulator and tear them off into conduction. We will have current now. We have motion of charge. So when we were talking about resistivity, and we were talking about the bounds of resistivity, we said that a perfect insulator would have infinite resistivity. No electric charge could flow through it because the electrons are bound. Well, guess what? If you try hard enough, you can make anything be a conductor. Okay? So this is often called the dielectric strength. Every material has a characteristic electric field, and if you exceed it, you will literally tear the dielectric apart. It will not be able to shield off whatever it's supposed to shield off without literally tearing apart. Okay? So you will find on your equation sheet, you will find a list of materials. What is their kappa value? What is their ability to do the partial shielding? So what percentage do they reduce the external electric field when they're operating properly, when they're able to actually do that? But there will also be different thresholds. It's labeled dielectric strength. It's literally an electric field, so I don't remember if it's volts per meter or newtons per coulomb. But it'll literally be an electric field where if you apply an electric field to it that exceeds that value, that dielectric won't work anymore. Okay? So that is what you are worried about. And that is a limitation for making the distance between the plates too small. Okay? If you make the distance between the plates too small, that does make the capacitor better, but it does make your electric field larger at any given voltage. And you had better hope that if you're working and applying a certain voltage to that capacitor and trying to charge it with that voltage, that does not exceed the dielectric strength of that material, because then the whole capacitor will get fried. It will literally get torn apart on a molecular level, and it's a material that won't recover. So an example would be air. Air has a dielectric strength, and this is a value that you will need in several of your homework problems, is 3 times 10 to the 6th volts per meter. If you apply that electric field to air, it will be torn apart. So you have a question on your homework where you compare lightning, which is the dielectric breakdown of air, with when you go to touch a doorknob and you have a little spark that jumps. That's also dielectric breakdown of air. In both cases, this value of the external field applied to the air is exceeded, but it's very different scenarios, because obviously your finger has to be quite close to the doorknob for this to work, right? Chances are you're not going to create a spark from here all the way to the doorknob, right? That's because you can't build up that much charge on your finger. So the little charge you can build up on your finger when you're scuffing your feet against the carpet, right, the triboelectric effect, that little amount of charge, in order, and that you can imagine that your finger is not a very good capacitor. Basically, the doorknob and your finger are the two plates of the capacitor. It's not a very big capacitance. You're not going to store that much charge, and therefore, in order to exceed this value, right, with a modest voltage, in order to exceed this value, your distance is going to have to be very tiny, right? So the distance has to go way down before the electric field exceeds this value. So you are going to zap the doorknob maybe, if you're lucky, like a millimeter away, okay? Lightning is a different story. Of course, you can have tremendous charge buildup, right? So if you can have tremendous charge buildup, and of course capacitor plates, so the cloud and ground basically are tremendously large plates, you can get a tremendous amount of charge buildup basically stored between the cloud and the ground. And it can jump a substantial distance, right? So that's why you don't have to worry about, it's the amount of charge that ultimately ends up transferring, right? And how many molecules get torn apart, that's going to affect whether it's dangerous or not. So you're not going to get killed by zapping your finger on a doorknob, but the amount of charge that jumps from one to the other is going to be substantial with lightning. So don't get hit by lightning, okay? So what happens here is that this stuff gets torn apart. You actually have flow of charge. Minuses from the dielectric go this way, pluses go this way. And if you have dielectric breakdown, you have a almost complete neutral, usually a almost or completely neutral amount of neutralization of the charge that's on the plates. So remember, the whole purpose of the dielectric was you had these charges stored on the plates. Those can be taken off and put on because they're conductors. But then you had this charge polarization, but that didn't really count because that charge belonged to the atoms in the dielectric. Well, of course, now we're talking about trying so hard that you literally pull them off. You literally pull these onto these, and you pull these onto these, right? So that's dielectric breakdown. Are there any questions on that? Yeah.
So if you have dielectric breakdown, does that mean that the capacitor doesn't work anymore?
Yeah, you've literally changed the dielectric on a molecular level, you basically have sent current through, you burned it, you dissipated power, it can often change the composition, and so you can't count on kappa being the same anymore, right? It's different for lightning, of course. If you pull apart a bunch of air, air is constantly circulating, so you can have lightning again later, because air, a fresh batch of air can always exist between the cloud and ground. But if we're talking about a solid dielectric, basically once you've pulled it apart, you fundamentally changed it. It probably won't work again.
So would it be, if you were doing like a circuit, would it be like an open?
It would probably be, if you created a conducting path through it, it probably would be more similar to a short circuit. That's typically if you like have a capacitor go out in like a electronic device, you accidentally apply too large of a voltage and you cause dielectric breakdown on one of the capacitors. Usually it ends up being a short, and what you have to do is you have to literally open it up, take it out, put in a new one. So it's basically when you fry something, usually it's because you dissipated power in something that you weren't supposed to. That means that for a resistor, dissipating more power than you should have, and this shouldn't be dissipating any power, right? This is not a resistor. We don't want current to flow from one plate to the other. But when you have dielectric breakdown, that's literally what you have. You have charge going across the plates. Question?
What happens at the very end of the plate? It's still uniform.
At the edge? Well, in our approximation, right? So we said that these are basically like infinite planes, and so if you want to talk about we call it sometimes the fringe electric field. They look, your classic dipole thing, but we ignore that. Most of the action is happening in the middle. Yeah. In fact, this formula right here actually comes from assuming that the plates are very, very large. So this is assuming that they're basically infinite. That's a game of physics, is you kind of have your cake and eat it too. You, for convenience, think of the plates as very large, even though they really aren't. Okay, so that's dielectric breakdown. If you were wanting to make a circuit, you would make sure that whatever capacitors you put in, you have some awareness of what dielectrics are in there and what dielectric strengths they have, and make sure that you don't ever apply too much voltage to them so that the dielectric strength would be exceeded, because then it's not going to work. Okay. Let me clear some space. Any last questions about that? Okay, so last order of business, some series and parallel caps.
Actually, I'm sorry, I have a question really quick.
Yeah.
On the voltage and the dielectric strength, voltage over meters. The 10 to the 6th power, it's whatever the K is you need to multiply by 10 to the 6th.
No. They're
Okay.
completely independent. Yeah,
Yes.
this.
On the equation sheet, I wasn't sure if that was just for that homework problem, or on the equation sheet kind of snuck in a 10 to the 6th power next to the voltage.
Oh, it was just giving that because, like, if they're all 10 to the 6, it saves you some writing, right? So instead of saying, they'll just say 3 here, right, for that. But I should mention that for air, this is the dielectric strength, but the kappa value is not 3. It's like 1.00, I forget, it's 5.9 or something. It's very small, which tells you that it's not a very good partial shielder at all, right? It's air being mostly empty space does not have, at a typical density, right, does not have very good ability to shield anything. So you get barely any shielding at all. But if you do have air in a space, it will eventually tear apart. So air, definitely would not want air as your dielectric if designing a circuit component. It's a terrible partial shielder, and it would break apart. So if you want a good capacitor, you want both values to be really high, right? Kappa means it's a really good partial shielder, and high dielectric strength means it won't tear apart for except under very extreme conditions. Okay, so let's talk about series and parallel caps. So let me remind you, we've of course talked about series and parallel before, so let me remind you, for resistors, the law is V equals IR. Now we learned such things as in series, current is the same through each resistor, but the larger resistor gets the larger voltage drop and power dissipated. Okay? So that's something we learned. Hopefully that's comfortable. The way I characterized this was that the larger resistor is the quote-unquote bottleneck, right? So if you have to go through everything, all the current has to course through every element, well, the thing you're going to have to pay the most mind to is the big obstruction in the way. It gets the largest voltage drop, so the largest motivation to get across that obstruction, and the largest power dissipation. In fact, I can remind you, in our 3 power laws that we have available, I recommended this one for series because